Thank you, G. Okay. So yes, let's talk about quantum. So why should you care? Here are the three reasons why you should care. So the first one is it's actually a practically relevant problem that's actually at the vanguard of computing. So that's what we're all here for at Fox, right? Second of all, if you're really into distribution testing, which I know you all are, you get to do it all again. Like you write a paper about distribution testing, you get to write another paper about the quantum version of the same problem. So it's twice the fun. And third of all, dare I say it, like I think the math is even more beautiful than the beautiful math we've already seen so far. So these are the reasons why I think you may like this topic. Let me start with the first one. So, you know, there's a lot of excitement in the news today about like quantum stuff and people are building quantum computers. So this is like one example from a Wave Hands group. You might have read about this in 2017. So they did this quantum teleportation experiment. Never mind what that is, but like there's some ground station at Nagari in Tibet, and there's some mission satellites in space. It's like 1,200 kilometers away, and they like teleport like a qubit from down here to up here. Okay, that's what the point of the paper is, to like demonstrate that they can do this. Now, so what does this mean? There's some particle that's in a quantum state. This is my picture of a particle in a quantum state, rho, down here, and then they teleport it up here. Okay, but of course, when it arrives up here, it's not exactly, I mean, it's supposed to be in the identical state, but it's not exactly the same state. And if you look at their paper, they're even like, well, on some days the moon was kind of bright, so like extra photons got into our satellite. So they're going to get like some corrupted version, copy of the state here, but they want to say that it's basically the same as the state that they teleported. So they have to check their work, right? They have to find out, like, what is the state of the particle that they got up on the satellite? Like, hopefully it's really close to this state of the ground. So they have to, you know, estimate the state or test the hypothesis that rho hat is the same as rho. Okay? Now, a little bit in contrast to what, so what they really want to compute, they're obsessed in quantum with this measure of distance called fidelity. Turns out that's basically just Hellinger squared, so we know all about that here. So yeah, they want to, let's say, estimate the Hellinger squared between this state and this state. Slightly in contrast to what Costin was telling us, I mean, if you don't have any assumptions, it's hard to do anything with one sample. So of course they, you know, if you just have like one sample from a distribution or from a quantum state, you can't tell what it is. So they managed to get 911 samples over the course of a month. And the real blocking issue here is time. Like it takes them 10 seconds to get one sample, and they can only work for 6 minutes a day. So they got 911. And then they estimated the Hellinger squared between this one and this one is 0.21, and they were like, great, that's very close. We can now write the paper saying that we did it.
So in how many dimensions is this? Like 2 to the 900?
Yes, this was actually a qubit, so the dimension here was 2. That's like n equals 2 for you guys.
But you have 900 of them. Oh,
yeah.
I see. So you have, can you treat it as 900 samples from one qubit, or is it?
Yes, yes. It's like a 911-bit string, except they're not quite bits, they're qubits. But
IID.
Yeah, the assumption is always, I don't know if it was really IID, but the assumption throughout this and throughout everybody's work here is that it's like IID samples. Okay, so that's a little bit about this topic. And now let me get into the main part of the talk, which is about relating it to classical distribution testing. Okay, so what is classical probability density testing? Well, we've heard a lot of that already today, but I'll just say the framework in a way that's appealing for me. So you have some unknown n outcome source of randomness. Is that a rho or a p? I can't. Okay, I think it's a p. Okay, so p. So we're talking about the classical state here. So you have some probability distribution on n outcomes, like we always have in this day. It's got some squiggly things over here, but think of it like an n-sided die. Okay? And then you take m samples from it, you roll it m times, and then or you can think of it as you get one draw from the product probability distribution, p to the m, and you put it into your algorithm x. And your algorithm, let's say, outputs a real number. Okay, so in Clément's introduction, that real number was either 0 or 1. You were like making a yes or no decision at the end, which is fine. So like maybe x is 0, 1. You're guessing whether p is the uniformly, the uniform distribution, or maybe it's a real number because you're trying to estimate the distance between some known hypothesis q and the true distribution p. Maybe you're trying to estimate the entropy, whatever. So let me just assume that your algorithm is outputting a real number. So let me go through an example. It's like actually the most basic example. We've seen it several times today, but it'll be illustrative for me to go through it again. So let's talk about testing the uniform distribution. So let's say you fashioned a die with n sides, and you like tried to make it like a uniformly random die, but of course you didn't do it perfectly. So you have some hypothesis that p is the uniform distribution. You want to test that hypothesis. Or maybe you actually want to estimate the distance between p, the thing you actually produced, and the uniform distribution. Okay, we've seen there's like 100 different measures of distance between probability distributions. They're all here. Actually, when the other distribution is the uniform distribution, chi squared and L2 squared are actually the same. So let's do that one, because then you get 2 for the price of 1. So let's talk about this problem, estimating the L2 squared distance between P, the unknown distribution, and the uniform distribution. Okay, so that's the task we want to do. Okay, well, you just write it down. It's this, sum of pi minus 1 over n squared. And with a little arithmetic, you see it's this. It's sum of pi squared minus 1 over n. Okay? So really, you just want to estimate this thing, sum of pi squared. And then you can subtract 1 over n at the end if you want. Okay, so how would you do that? This is called the collision probability, by the way. Let's say I give you, you can't do much with one sample. Let's say I give you 2 samples. Then what would your algorithm x be? Well, I claim there's a very natural algorithm, x. Just this. You're given a sample a, b from the twofold product distribution, 2 samples. Just output 1 if the samples are the same, and output 0 if they're different. And what is the expectation of your outputs? Think about it for 1 second. It's this. Sum over I of pi squared. It's the probability the 2 samples are the same. And that's great. The expectation of your output is the thing you're trying to estimate. So fantastic. Of course, to say that it is good with high probability, you need to bound the variance, which you can easily write down explicitly. But it's a bit large. So this, if you just use 2 samples, you won't get an accurate estimate with high probability. Of course, it's just 2 samples, right? So you actually get n samples in life. So great. Let's say now I give you more than 2 samples. I give you some m samples. What should your algorithm x be? Well, I claim another very natural thing to do is just take the m equals 2 algorithm and average it over all pairs of samples. And another thing about that is the expected value of the outcome is, well, it's always all pairs of samples have expectation sum of pi squared. So does the average of m choose 2 possibilities. Great. But the variance goes down. And it's really easy. I mean, like any algometry, you can just work it out what the variance is. It's a bit tedious, but it's straightforward. And that's great. And then you do the usual thing. You maybe bound the variance in terms of the expectation. You apply Chebyshev's inequality to say that the random variable x is very often near its expectation. And to make a long story short, you get this. So we've seen several times today that with something like square root n samples, you can actually distinguish whether the L2 squared distance that you're trying to estimate between P and the uniform distribution is greater than or equal to this quantity or very slightly less than that quantity. So you can really estimate it very accurately. And the reason I didn't just write epsilon here is because most people are in love with the L1 measure of distance, which you can relate to L2 squared distance by Cauchy-Schwarz. So I guess if the L2 squared distance is bigger than epsilon squared over n, then the L1 distance is bigger than epsilon. Okay, so this is how you get this famous result that you can test whether a distribution is far from uniform in total variation distance, or equal to uniform distribution, or even close to it in L2 squared with something like square root n samples. Okay, so in some sense that's review, given what we've done today. But I want you to remember 2 things about what I've told you here, 2 slightly different things. One is the algorithm. The algorithm, in some sense, was to take your m samples and average over all transpositions, tau and Sn, of the 0-1 indicator that applying tau to the samples leaves them unchanged. I mean, I phrased it as you look at all pairs ij, whether the I sample equals the j sample. It's just the same as saying, you look over all pairs ij, if swapping the ith and j samples would change nothing. But I'm going to want you to think about it that way later. The other thing I want you to take away is that, an algorithm here, I think of it as just, it's a random variable. X, where the randomness of the random variable is based on the samples, the m-fold product distribution of P. Okay. So let's take a look at the classical probability density testing picture when m is 1. I'll sort of summarize what we've seen. In some sense, it's without loss of generality to look at m equals 1, because you can either say, oh, I get m samples from P, or you can say I get 1 sample from the product distribution P to the n. So let me just go back to having 1 sample for a second. And let's just look mathematically at what are all the objects on the top part of this slide. So P, it's an n-dimensional vector. It's a probability distribution, and that means it's non-negative, and the P's add up to 1. And X, well, I said it's like a random variable. You can also think of it as an n-dimensional vector. Like for each outcome, I between 1 and n, xi is like the real number that you output when you see variable I. And what is the expectation of x under P? It's the inner product of P and x. Okay, sum over I, pi, xi. And we're always computing variances in these things, which is equivalent to computing expected value of x squared. So what is the expected value of x squared? Sort of like the inner product of P with x squared, where I just mean like the component-wise squaring of the vector x. In other words, it's sum over pi xi squared. Okay, so nothing new here. This is just basic probability. But of course, I formalize it this way because I can now tell you what is the deal with quantum probability distribution testing. And to change the picture from classical to quantum, you just have to do one thing. Every time you saw vector on that slide, just replace it with symmetric matrix. Technically Hermitian matrix because they're complex, but I try to minimize complex numbers, so just say symmetric matrix. Okay, so just take a slide, replace vector with symmetric matrix everywhere, like this, and like now you know what is quantum probability distribution testing. Yeah?
So you also have to replace all the p's by rows?
Yeah, you have to take a little bit of a serif off the p right there to make it into a row. Yeah, so let me say it a bit more slowly. So in quantum probability distribution testing, you have an unknown source of randomness, now called rho, which is the state of some particle or something. This is the m=1 sample picture. And the state, by definition of physics, is like an n-dimensional symmetric matrix. And same deal, it's non-negative, by which I mean it's positive semi-definite. And instead of sum of pi equals 1, it's sum of pii equals 1. So the sum of the diagonals of this matrix is 1. And your algorithm X is also a matrix instead of a vector. And it's just any old symmetric matrix. But it's, again, true that the expectation, your algorithm also outputs a real number. That's not changed. And for a given algorithm X and a given unknown source of randomness rho, the expected value of the algorithm's output is kind of this. It's like the inner product of rho and X, like the matrix inner product. Like you just dot product the matrices together. So it's sum over ij of rho ij xij. And if you want to understand the variance of your algorithm's output, it's, you can look at the second moment, and the expected value of x squared is the same thing, except you replace by x squared. And here I really mean like the matrix x times itself, the matrix squared. Okay, so in principle, like you now know everything you kind of need to know in order to do quantum probability distribution testing.
Can you say what the matrix X represents?
I certainly can. Let me just add that one thing. If you have m samples, then it's the exact same picture, except that, the new source of randomness is rho to tensor power m, or like the m Kronecker product of the matrix rho. So this is now like an n to the m dimensional matrix, and your algorithm will also be an n to the m dimensional matrix. But yeah, let me answer. I can answer your question. I keep thinking it's going to be the next slide, but it's one more slide. Let me just say that in the quantum picture, if you want to go back to the classical picture, then just take all those matrices and assume that they're diagonal matrices. If you assume that they're diagonal matrices, rho and x, then like everything exactly turns into the classical case, where the pi's are the diagonal of rho. Okay, so right. So what does this mean? Like, what's going on physically? I told you like the mathematical framework you use to start analyzing things, but like, what are you even doing? So this state rho, this matrix, is the state of a particle system. And it's the laws of physics and everything, like you, me, a photon, has a quantum state, which is, it's a matrix, a PSD matrix where the sum of the diagonals is 1. We call it rho. So like one photon has a state, or if you have like 4 photons and they're like hanging out together, those 4 photons jointly have a state that's defined by a matrix. And n is somehow the number of basic outcomes. So if you have like 1 qubit, then n is, the dimension is 2. Or if you have like 4 photons, the dimension is 2 to the 4, 16. Okay? So this is the state is like, in this case, is a 16 by 16 matrix. In contrast, if you're like have probability distribution testing over 4-bit strings, there's still 16 outcomes, but the probability distribution is the 16-dimensional vector. Now it's a matrix. Okay, so that's the thing. It's like the thing that is received up there on the satellite by the teleporters. Now, what's the algorithm? So the algorithm in quantum is called an observable, and you should think of it physically as some measuring device. It's like some device, maybe even like a quantum circuit with like some gates and then like some measuring devices. This I googled for a picture of photon detector, and it gave me this black box. So that's what I put there. It's some measuring device that you like literally feed the particles into, and then it spits out, it has like a readout, which is a real number. Okay? And so the physical meaning of what's going on, but it too has it's defined by a matrix. Every measuring device you might build is defined by a matrix. And yeah, the story is you put the particles into the measuring device, and it like outputs a real number. And that's physically what's going on. And I can tell you, as a function of the matrices rho and x, like what is the probability of seeing any given number when you feed the particles rho into x. It has something to do with like the eigenvalues and eigenvectors of x, but don't read this. Instead, I just want you to remember this. Like, if you, the algorithm designer, designs this measuring device with matrix x, you can design one for any matrix you want, and you plug into it some particle with state rho, then the expected value of the outcome of your measuring device on these particles is like the inner product of rho and x. And same story for if you want to compute the variance. And since in this testing and learning game, we're usually just concerned with maybe the expectation and variance of our estimates, it's kind of enough to remember this.
Can you build any matrix X?
In principle, yes. So I mean,
does it have to be PSD? Like, what are the constraints?
It has to be Hermitian, symmetric. That's it. Yeah. Actually, you can even do more things than this, but like this is a pretty good picture. Yeah. If your algorithm takes in quantum particles and outputs a real number, then like you can basically think of it as this. Okay. Great. As we've seen, Clement also talked about this. We're going to talk about lots of different issues. We might want to test some property of our state or test the hypothesis that rho hat is the same as the thing we prepared, rho. But the baseline is always learning rho. That's maybe the most basic problem, and like it's the baseline for all your future results. So it really means just estimating all the entries of this matrix. There are n squared of them. And this is sometimes called quantum tomography. It's a fancy name. I don't know why they invented that. It should just be called learning a quantum state. And let me just say there's a naive method. If you kind of use x's that look like this, and you just imagine like dot producting like these x's with the unknown matrix rho, you kind of learn all the entries of rho separately. There's n squared entries to learn, and in order to get a good overall estimate, you kind of have to learn each entry to some like accuracy that's like 1 over n. Let me just say, long story short, there's like a naive way to do it that uses n to the 4th samples. So it's polynomial in n, that's good. And they actually, in practice, use some very naive thing like this. Partly because these are really simple x's, so they're pretty easy to like literally physically build. But like most of us, I'm not going to be too concerned about the complexity of the algorithm per se. I'm just going to be mainly concerned about the sample complexity. So it turns out that this is not sharp. So my co-author John Wright and I, and also this paper by Ha et al. In 2015, we showed that actually the correct answer is n squared. N squared over epsilon squared samples are necessary and sufficient to learn an unknown state rho, which is an n by n matrix, to epsilon accuracy in like the L1 distance. Okay. And it's kind of reasonable because there's like n squared like unknown numbers in this n by n matrix, so maybe it's like sensible that it takes you n squared samples to learn it.
So this trace L1 has to do with this Hellinger distance you mentioned earlier?
So again, there's like multiple choices of distance in the quantum world. So this distance, the trace one, is the analog of TV. It's literally the matrix L1 norm of your estimate minus the truth. And it has the same kind of operational property as TV. It's like the best probability with which any experiment can distinguish two states. But on the other hand, quantum people are really into this thing called fidelity, which is the analog of Hellinger squared. So we know the answer for that too. It's n squared over epsilon. Oh, except we don't know there's some log factors we can't get rid of. So the baseline for all these tasks is n squared samples from the state. And so you may try to do better than that for analyzing other properties of rho.
So that's right. So that's allowing measurements on the whole thing, right? So if you force yourself to do independent measurements, then you get back to the naive thing? Or?
I don't know the correct answer, but Thomas makes a good point, which is that a lot of algorithms work in sort of a simple way where they like take one sample, like one rho, and they measure it with 1x, and then they take another sample, and they measure it with 1x, and take another sample and measure it with x, and then they collate the real numbers they got. That is not the most powerful thing you can do, but often people do it in practice because it's easier. But here we're imagining that like you can take n equals n squared samples from this thing. You have like n squared copies of the particle, and you feed them all into one gigantic algorithm, which you can imagine has like n squared inputs. So yes, you can measure all of them simultaneously. Okay, so let me tell you a way that I like to think about this quantum learning and testing scenario. I think it's easier to think about. My co-author John doesn't like to think about it this way, but he's not giving the talk, so I'll tell you how I think about it, because it's going to make it seem a little bit even more closely connected to classical case. So let's take a look at the players in this slide. Particularly rho, the unknown state that we're trying to learn or test or whatever. So, okay, a symmetric matrix rho counts as is an example of a state if it has two properties. This first one is saying that rho is PSD, which is equivalent to saying that rho's eigenvalues are non-negative. Rho being symmetric or Hermitian has real eigenvalues. In this condition, if you know a little linear algebra, is saying that the trace of rho is 1, which is equivalent, as it turns out, to saying that rho's eigenvalues sum to 1. So this is great. Actually, the property being a quantum state, rho, is just equivalent to saying that your eigenvalues are non-negative numbers that add up to 1, so they're a probability distribution. So a symmetric matrix is a quantum state if and only if its eigenvalues, which I'm going to henceforth call P1 through Pn, form a probability distribution. That probability distribution doesn't fully define the state, but the one thing it's missing is the eigenvector. So any matrix whose eigenvalues form a probability distribution, when you put it together with associated eigenvectors, defines a quantum state. And I really like to think of a quantum state rho as a probability distribution over the eigenvectors. Okay? So these are, you can assume they're orthonormal eigenvectors in n-dimensional space, and you should really now kind of think of the state as a probability distribution over them. So like when you get a sample, it's kind of like nature, emits this vector vi with probability pi. Okay? And you should bear in mind that the algorithm, or you, don't know the p's and you don't know the b's. So it's kind of like the classical case where you have this unknown probability distribution. But there are also these vectors at play, which are like an unknown orthonormal basis of n-dimensional space, which you also don't know. If you're trying to learn rho, you have to learn both of these objects at the same time. And furthermore, you can't just look at the vi after the particle, if you will, emits it. You can only do this thing of plugging it into an algorithm x. And let me just say, if you look back at the rules I told you a couple slides ago, the situation is as follows. Condition on, let's say, the quantum source, outputting vector vi, what is the expectation of the algorithm's readout? It's like this thing. It's like the overlap of vi with x applied to vi. So kind of the expectation is you apply your algorithm, which is like an operator on vectors, to vi and measure its inner product with vi. Okay, so that's a fact that we'll use later. Okay, so it's really you have an unknown probability distribution on vectors, but you can't look at them. You can only kind of access them in this weird way by specifying a matrix which acts on them, and the expectation of what you see is given by this formula. Actually, that's the picture when you just get one sample. What is the picture when you get 5 samples? Well, the picture when you get 5 samples is, it's you get 5 draws from this probability distribution on vectors. But there's a bit more of a twist, which is that it's not just those 5 vectors sit there in space. Their joint state is the tensor product of those 5 vectors, which is I guess an n to the 5 dimensional vector. And you plug that n to the 5 dimensional vector into an n to the 5 by n to the 5 matrix x. Okay, so it's getting a little bit complicated here, so hang in there. Okay. So there is really nice analogs, therefore, between the classical world and the quantum world. So in both cases, we have a probability distribution, P1 through Pn. There's a little twist, though, which is that in the quantum world, this P1 through Pn are the eigenvalues of a matrix, and eigenvalues are not inherently ordered. So you really only have a multiset, P1 through Pn here. So every quantum problem, let's say that just involves the p's of the unknown state, is really analogous only to one of these symmetric problems that we've talked about in a couple of talks. Okay? On the other hand, of course, there are no vectors in the classical world, but just in the quantum world. But other than that, we have this really nice dictionary between the two problems. So there are plenty of problems in the quantum world where you actually just care about the p's. You don't really care about the v's, even though they're there. So for example, the rank of a quantum state is the number of non-zero pi's. That's quite important physically, and it corresponds to the support size problem in the classical world. If you take the entropy of the pi's, that's called the von Neumann entropy, and it also is interesting physically. So people are very interested in estimating the entropy of an unknown quantum state, and it only depends on the p's. Yeah.
So is it the case, just to try to map it, estimating the van der Waals entropy, is it like n squared over log n or something like that?
We would like it to be n squared over log n. So John got it to n squared. But yeah, the dream that we're thinking about is can we get it down to n squared over log n?
But it's not so, if you can learn, you don't, I mean, isn't that n squared over epsilon squared just basically learning?
Yeah, you have to, I don't know like exactly what error metric you need to learn in order to effectively estimate the entropy. Like, so, you know, John was very careful about the epsilons and things in his work on that. But good question. Yeah, the problem there, which is open, is to get it down to n squared over log n in light of, you know, the toxicity.
Is there a lower bound of n squared over log n that would follow from the classical case?
No, we're not that good yet. Yeah. Yeah, another analogous thing is like the most random distribution. In the classical world, it's the uniform distribution. In the quantum world, it's called the maximally mixed state, and it's when rho is just got 1 over n on the diagonal. That's 1 over n times the identity matrix. Okay. And again, all the distances you have over here, they have like a nice analog in the quantum world. So really, this is, you know, if you want to do it all again, as I said, like just take what you've done here, as long as, let's say, it's a property, symmetric property, try to do it over here. You can take a shot at it. And there's like more great problems over here if you get like the vectors into the picture as well.
So like in the case of like the maximally mixed state, what eigenvectors are being applied?
Good point. So like the quantum states, eigenvalues are not, eigenvectors are not necessarily uniquely defined. And that's one reason why it's not always the best way to think of rho as like probability distribution on orthonormal vectors. Because in this case, like those eigenvectors are not well defined. So really, like if you're trying to, you know, decide if your estimate is like close to the, you know, if you want to be interested in how far like rho is from something, you really have to work with the matrix rho and like not the actual eigenvectors. Yeah.
So,
Yeah.
So what happens in a maximally mixed state in an experiment? Do you actually pick a random vector v, a random unit vector, and then observe v transpose xv?
Yeah, like anything you do, you can just actually imagine that there's like some fixed orthonormal basis and like run the picture I had in mind.
No, but the challenge is that might, like your interpretation should not depend on the orthogonal basis, right?
It won't though, because you're picking these guys at random. It's maybe not so easy to immediately see. Or if you don't like that, you can like go back to just, you know, before I give you this interpretation, you can just go back to this interpretation. So when rho is the maximally mixed state, like the expectation of the algorithm is just the average of the diagonal elements of x. Okay, so yeah, so let me tell you like one more example along these lines about you know, designing maybe a non-trivial algorithm. So let me look at the analog problem that we talked about at the beginning, like estimating the distance of an unknown state to the, in this case, maximally mixed state. Okay, the identity matrix over n. So this is what we're curious about. We have this unknown state rho, and we're interested in this quantity. It's Frobenius squared distance, or L2 squared distance from the maximally mixed state. And if you just calculate for 1 second, it actually only depends on the eigenvalues of rho. And it's literally exactly this. It's actually sum of pi minus 1 over n all squared, just like before. So actually, we have the exact same target. We're trying to estimate this quantity, same as in the classical case. In the quantum world, it's not called collision probability. It's called quantum purity, but they had a name for it as well. So we ask ourselves the same question. Let's say we have 2 copies of the particle. We need to design an algorithm X. What should we do? Well, you can think of rho as emitting. Here, I hope you're a little bit maybe familiar with tensors. If not, just try to play along. So you can think of rho as emitting a pair of vectors, but like tensored together, VA, VB, with probability PA, PB. And remember, both these probabilities and the vectors are unknown to you. You sort of actually don't care about the vectors because you're only interested in this, but anyway, they're making your life potentially difficult. So you have to design an operator X that acts on such vectors, that acts on Cn tensored twice. And what should you do? Well, in some sense, like X, okay, so X does not know the vectors v1 through vn, but in some sense, it does understand the tensor structure of the space. So what you just do is you let x act by swapping the tensor components. So I assure you, this is like a well-defined linear operator on Cn tensor 2. It's just defined by, on, let's say, tensors of the basis vectors by swapping them. You can extend it by linearity to act on the whole space. And long story short, it also has the property that like x applied to VA tensor VB is the swap of VB tensor VA. That just works for like any tensor, even if x doesn't like know the v's. Okay, so this is just a fact that x kind of swaps the outputs of rho. Great. So that's pretty cool because now we can say like condition on rho outputting some pair VA tensor VB. What is the expectation of x? Remember I told you like it's you like let x act on the thing and then you inner product that with the thing itself. So x acting on VA tensor VB is VB tensor VA. And then like the inner product of these two guys, it's actually I guess the square of the inner product of VB with VA. Anyway, these are like orthonormal vectors, the v's. So this is just 1 if A equals B, if this vector equals this vector, and it's 0 otherwise. Yeah, so that turns out to be some just simple linear algebra. And this is awesome. It's exactly like the classical case, right? It's great. So like the expected value of the output of your quantum algorithm is sum of pi squared. Perfect, just like we wanted. There's a little bit twist, though, which is why it's not identical to the classical case. So we've got the expectation, and now we need to compute the variance. We need to compute expected value of x squared. So let's just do the same thing for x squared. What you see, we write the same thing, but now there's something a bit funny. What is x squared? It's the identity operator. You like swap the vector components, tensor components, and then you swap them back. So this is just equal to VA tensor VB, inner product with VA tensor VB. So it's always 1. Okay? And this is in contrast to the classical case. The classical case, what you would be doing here is you'd be looking at the expectation of the indicator that the two samples are the same. Square of an indicator is the indicator itself. So the expected value of x squared in the classical case is again sum of pi squared. Here it's just always 1, which is bigger. This is actually the source for why the quantum version requires more samples than the classical version. Now we don't have to actually try too much because again, okay, the variance is large, but this was still the case where I just had 2 samples. So again, of course, I'm allowed to like take lots of samples, and that will make the variance go down. So if I have more than 2 samples, what should my algorithm be? Well, you won't be surprised. It'll be the same idea as in the classical case. We'll literally let x, our algorithm, if you will, be this. We're just going to like, now we have like m vectors tensored together, and we're going to average over all pairs of positions, I and j, of the swapping operator. Okay, so I actually introduce some more general notation. If I have some permutation pi on m things, r of pi means the operator on Cn to the m, which permutes the tensor components according to pi. Okay, so, but we're only going to use it here for transpositions. And now the expectation is still sum of pi squared because, like, it's the average of a bunch of things whose expectation is sum of pi squared. And for the variance, we need to compute x squared. Okay, so this is x. This is a matrix. It's an average of a bunch of matrices or operators which swap tensor components. So the x squared is like you average over all pairs of transpositions of what you get when you swap, tensor components tau, and what you get when you swap the tensor components associated to rho. And if you first swap according to tau, and then you swap according to rho, it's the same as swapping according to the product, rho tau. Or sigma, I should be saying sigma everywhere, sigma tau. And that's nice. And actually, this is actually a little bit of the entry into like where some of the math comes in. This is actually just follows from the fact that R is a group representation of the symmetric group. It's a map from the symmetric group to operators on some space which respects the group product. But anyway, never mind about that. Right, so if you take 2 random transpositions, you multiply them together, sometimes you get the identity if they're the same. If they're disjoint, you get something of cycle type 2,2. And if they overlap on one point, you get something of cycle type 3. So this operator is some average of these kinds of operators where these coefficients are slightly annoying to compute, but you can compute them. Good. So now we have to just compute the expected value of this operator. And let me just tell you, for any operator that looks like this, the average of like doing swaps, or sorry, the average of doing permutations over all permutations of a certain cycle type, it's like kind of like fun exercise to show this fact that, let's say you're averaging over all permutations of the tensor components with cycle type 7 cycle times a 4 cycle times a 2 cycle, then you can easily figure out that the expectation of what you output is like this thing, this symmetric polynomial of the PIs. It's sum of PI to the 7, sum of PI to the 4 times sum of PI squared. Right? This is 7, 4, 2. So in fact, you can see our original algorithm, which like averages over all transpositions. That's why it's another reason why its expectation is sum of PI squared. Yep. Oh, okay, got it. Yeah, I'm almost done. Good. So you can just bound the. So with this, you have enough information to like compute expected value of x squared and like do the whole same game and bound the variance and Chebyshev and so forth and so on. And here's the long story short. It's the exact same result as identity testing to the uniform distribution, except instead of square root n, you have n. Okay, so you actually get the same square root savings over the baseline, which was n squared. Great. And in fact, in this paper, we get like the much more general thing of the exact same result for testing closeness in L2 squared distance of 2 unknown distributions. Unknown quantum states, I should say. And finally, an earlier paper of me and John showed that n over epsilon squared samples are sufficient, or are necessary.
So when you say same, you mean n samples?
It's the same, yeah, same number of samples, yeah. It's cool. Yeah, it's the same number of samples. So you can get the same result here for estimating the distance between 2 unknown states, rho and opposite of rho, with n over epsilon squared.
So it's not just the case that we can take the classical and replace n by n squared, because that would be n to the 4th.
Yeah, like if I take this to the classical world, do I get I cannot get improvements, right?
Oh, sorry. Okay, so what you can do is you can get this for like L1 epsilon versus identical in the quantum case with this many samples. That's like in the classical world. And you can also get the precursor to this, which is like tolerant testing of L2 squared with that same number of samples. Okay, so I'm basically out of time, so maybe I'll just skip to the end, which is to say that I promised you there would be like beautiful math, and there is. So you get into representation theory, and like you get all this cool stuff with like Young diagrams and random matrices and non-crossing partitions and like free probability and Tracy-Widom distributions, and like it's really great. So like there's so much like awesome math that goes into like the event stuff. You'll really like it. So if you want to learn more, I wrote a survey about it with John, and I'll stop there. Thanks. Yeah.
At the end, I didn't understand why did you take these permutations and things. So once you form the pairs of the density operators,
yeah,
then you just calculate this expectation value, and then you were averaging the whole thing together.
Yes.
And
well,
at this level, like you kind of have a classical outcome. So why does it be like classical averaging, and you have the channel bound and everything?
See, I'm just trying to totally get the question. You kind of need to understand that you understand that like what is the expectation of what you get from like one swap and the variance from you get from one swap, and then you have to like compute what happens when you kind of average these swaps over all pairs, and there's some calculation there.
Yeah, but can I just look at thing as like what is the outcome of one pair thing that you can just think about it now as like a classical random variable, right?
Yes.
You get two quantum states, who cares? But you, at the end of the day, get out a classical random variable.
I see. Like the algorithm doesn't like, the quantum algorithm doesn't like do the kind of transposition algorithm m choose 2 times and get like m choose 2 readouts and average them. Instead, it does this thing which is like a little bit inherently quantum, so I'm not sure what to say except that like the algorithm it uses, the x it uses, is like the average of all these like tensor swapping operators. So you kind of have to compute like the variance of that big X.
Yeah, but why don't you just do it classically? Like, then seems that you will get better results.
Yeah, I'm not sure I can really say in a short amount of time an answer. But yeah, well, we have a lower bound that says you can't do better. But yeah, I'll try to answer it. Not over the.
I've got a much more basic question. So you said that classical is basically like equivalent to the case where it's diagonal. Would there be any advantage of using a quantum algorithm to do classical distribution testing?
Yeah, there's work on that. Not super familiar with it, but there is like a bunch of work on that by Lee and others. I know less about it than I should. Okay, thank you.